Hello, my name is Rafiqul Gani. Welcome to this lecture, wherever you are. This lecture is actually a recorded lecture from the Sargent Medal lecture that I gave on 17th June. I would like to thank Professor Ignacio Grossman, who actually chaired this webinar session, and also ICAME for initiating the Sargent Medal and also for organizing the webinar. So first, let me say that I would like to dedicate this lecture to the achievements and the contributions of Professor Sargent. He was actually my supervisor for both my master's and PhD project at Imperial College. The title of this lecture is Models, Modeling, and a Systems Approach to Model Development. Before I start, I would also like to acknowledge that the recognition I'm getting is also due to the work done by my former master's and PhD students between the period 1984 and 2017, when I was a faculty member at the Technical University of Denmark. Also, I had a lot of work done in collaboration with partners from academia and industry during the period 1980 to now, and I would also like to acknowledge their contribution. Throughout these lectures, I've used ideas, methods, concepts developed by others, and I'm presenting them in the way that I understand them. I've not, probably I've not mentioned everybody in here, but if there is somebody missing, my apologies. So let me start with what is process systems engineering. This was defined by Professor Sargent and Professor Takashima in PSE conference meeting 1982. According to them, process systems engineering is all about the development of systematic techniques for process modeling, design, and control to solve various types of problems. The problems are related to, as you see in the figure, which is the main work, I would say, of the engineering domain that we represent, chemical and related engineering. That is, we take available resources, convert them into useful products that we need through processes that we design, operate, control, and so on. So modeling, design, control, all the problems that we would like to solve in a systematic manner is related to this. Also, Professor Sargent proposed a systems approach, which he defined as some formulate their problem or some useful simplification of it in precise mathematical terms, then seek to exploit the mathematical structure to obtain an effective algorithm, while others seek insight on the problem structure from physical intuition. Throughout this lecture, and also throughout my career, these two definitions have always been the basis for most of my work. So I would like to thank also Professor Sargent for introducing these concepts to me. The core topics or fundamental topics of process systems engineering, most people will agree, are the 5 topics listed on the column 1. That is numerical analysis, computer science, synthesis, design, optimization, and systems and control theory. It is important to note that for all of these, modeling is a subtopic. So why do we need these topics? These topics help us to develop methods and tools. So for example, numerical analysis and computer science results in simulators, data analytics, synthesis, helps us to develop product process synthesis methods, design, product process, design procedures, optimization, and so on. And then the application of these methods and tools is the outcome, that is the last column. So if we have simulators, data analytics, we understand the behavior, we understand the intelligent systems. If we have methods for product process synthesis, we are able to synthesize molecules, materials, process flow sheet. If we have the process control strategies and algorithms, we are able to process and do plant-wide control structures, controller design, and so on. But in all of these, modeling is a subtopic. So let us look at the how to solve problems with models, or why do we need models for problem solution. On the right, we see the kind of problems we would like to solve: design, production, planning, safety, many more. On the left, we see the systems for which we would like to solve these problems. That is the process, the product, operation of the process, use of the product, environment, the effects on the environment, the business, and so on. So how do we solve these problems? For the systems that we see, we try to collect all the information in terms of knowledge, in terms of data. And if we have sufficient information, as the systems approach had said, then we would find a way to solve these problems. However, in most realistic cases, there is not enough knowledge or data. And when that happens, we need to study the system, understand the system, develop a model or models. And then we solve those models and add the missing information. And then after that, when we have sufficient information, we develop methods to solve the problems. So the model-based systems contain models, data, numerical solvers, algorithms, including methods, workflow, data flow, and many more. Examples of model-based systems: process synthesis tools, process simulator, control monitoring systems, planning scheduling systems, and many more. The role of modeling should not be just, note that the role of modeling should not be just to replace the experiments. There's much more, and I will discuss this as we go along this lecture. So what is a model? The book by Hangus and Cameron on modeling has defined this nice, given this nice definition. Model, it is a pattern, plan, representation, or description designed to show the structure or workings of an object, system, or concept. It could also be a study of a miniature of the actual. The model objectives need to be clearly defined. From this figure, which is also taken from the book, one can see that on the top, the reality is the system. At the bottom, we have the model, which is a representation of the system. The question is, what are we capturing in the model? Are we capturing all the essential parts? Are we sure that we are not making any mistakes? Are we identifying all the required characteristics? These are all related to the understanding of the system, definition of the objectives, and so that we can actually capture what we need for the model. And the question also is, do we need everything of the system? And we will see that we need different parts of it at different times. So since we are talking about our engineering domain is chemical, pharmaceutical, petrochemical, agrochemical, food, all related to chemicals. So on one side, we have chemicals that you see. that can be single molecules or a combination of them. They form products, but these products are made in a process which we see on the right-hand side. So the chemicals behave in a certain manner in the process. Also, the application of the chemicals-based product, like a solvent or a refrigerant, will be used in a process. So in order to understand the system, we need to understand the model and the behavior of the chemicals within the process or the product. So what do we need? We need the models and data, of course. When I talk about models in this lecture, I also mean data, not just equations. So if we think of that, we have a process represented by a flow sheet, which consists of unit operations, and we want to also calculate the costs. We also want to look at the environmental impact, performance, control, everything. At the core are the models related to what is the phenomena occurring, what is the mass transfer, how is the reaction occurring, etc. And at the same time, if there are chemicals in different phases, we need to know the properties of those chemicals. So a wide range of models and associated data are needed to solve a wide range of problems. And we will see why this is needed. So then let's look at, we have defined what is a model. Now, what is modeling and how to obtain and develop models? So modeling, in my view, the process of generating abstract or conceptual models. It is representing reality with virtual reality for a process. What we need in order to develop model or in modeling is a good understanding of the system and very clearly define the model objectives. So here is an example of, let's say, use of developed models, or in another way, sometimes it can be called also modeling. And if one thinks of what is a process simulator, I think most engineers know what a process simulator is. It is one of the best or most used developments from the process systems engineering community, I would say, because at any time on Earth, somebody is using a process simulator. And what is happening in a process simulator? It already has a collection of models in a model library. If we want to simulate a process, we identify from the library or retrieve from the library the models we need for our process. And if we are able to find them, we take them, we represent them in the figure that you see, and we can do the simulation. So we do not need to derive the models or the equation. Somebody has done it for us. We just use the model. That's a very common way of doing modeling. But what happens if the model we need is not in the library? Then we need to understand the operations in the process that we want to study, and then we need to derive the model equations. That is still at the level of process operations, but if we want to develop at a lower scale, like the phenomena, what you see in the figure on the right is actually the cloud after an explosion, the gas cloud after an explosion. Can we model that? And what is needed to model that? So that's an example of the phenomena modeling. Again, a good understanding of the objective of the system and the model objectives are needed. And we can also see in this last example on the right-hand side, it depends also, this is also related very much to the weather pattern and things like that, that the cloud is not going to be stationary, it's going to move, and which direction it will move, and what will happen on its path. All these things can also be looked at. And then through this example, now I want to show that just having the model equations is not enough. Sometimes more than the model equations are needed. So let's say that we have a reactor where a reaction A going to B takes place, and the reacted A is coming through the stream F1, and the product is going to, the reactor product is going to go from F2. The reaction maximum conversion is obtained at 50% A at 340 K. Now to extract the product B from A is not easy. So we have to put a solvent, which is F3, and then solvent will create two phases and will take B away from A. So F4 is the stream that will have only A, and F2 is the stream which will have the solvent and B. And then A can be recycled back. And we can model that. There are two phases. This reaction is occurring, mass coming in, mass going out. We can do the mass energy balance and develop the model. What I will show is that enough? It is not, because if we want to study this operation and study the solvent effect, we need to be able to use the model and operate the reactor virtually through the model. So which means that we need a operation or design model. That means we need to say that initially we will charge the feed. So F1 will be open, F2 will be closed. Then we will close F1. Then we will heat the reactor until we have 340 K, and we will control the reaction or the operation at 340 K. And then when the reaction has taken place, we will add the solvent, and then we will extract B by opening F4, and then so on. Sorry, I said solvent will go out in F2, but the solvent will go out in F4, and so on. So in addition to the actual process model, we also need an operation model which will tell at what time what has to happen in the operation of the process. And let us also see what is the relationship between the process and the product and how the model will change because of that. So within the engineering domain, again, that we are involved with, as we said, we are involved with the conversion of resources to products through a process, and therefore we have to satisfy the conservation of mass, energy, momentum, which means that we have balance equations. If it is at steady state, the left-hand side will be 0. Otherwise, there will be accumulation. But in the process, in addition to the balance, we also have constraint equations. That means some conditions have to be satisfied. If there is an equilibrium condition, then the condition for equilibrium between phases have to be satisfied. If there is chemical equilibrium, the condition for chemical equilibrium has to be satisfied. So we have also constraint equations. And then you see that in both the balance equation and the constraint equation, there is the symbol theta. Theta here is representing what we call conceptual variables, which is actually the thermodynamic variables. The interesting thing is that these conceptual variables, although we can get measured values of them, they cannot actually be measured directly. They are measured indirectly. On the other hand, the variables that can be measured directly are called measurable variables or the intensive variables, which are the temperature, pressure, composition, the moles, species ID, and so on. So the idea is that if we know the temperature, pressure, composition, the species molecular structure. Then we can calculate the property theta, or the conceptual variable theta, which actually affects both the mass balance and the constraint equations. So in a process model, we need all the three equations, the balance, the constraint, as well as the constitutive equations, which are actually then the process models. Sorry, the property models. But in product, we are actually looking at the behavior of the product only. So there we only need the constitutive or the property models. However, if we want to look at the application of the product in a process, then that process application process may involve a process model with balance equations and so on. So for example, as I mentioned before, a solvent, if it is verified whether the solvent works or not in extractive distillation, we need the process model, which is based on conservation of mass energy. On the other hand, if we want to know whether a drug works on the body or not, that does not involve a process like a extractive distillation, but it involves solubility and diffusivity and so on. So there are different ways to look at the product model and its application. Another thing to note is that the theta that we need, for which we can provide either measured data or a model. And if we provide a model or data in the simulator, when we want to solve the balance equation or constraint equation, we can use only one value. That means only one property model can give us the value of the theta we need. We cannot use more than one theta value for the same property. That is also very important because in many simulators, in order to provide more flexibility, they offer more than one property model. But more than one property model would mean that if there is a stream connecting two unit operations, they will have two different values. While numerically, the problem may not be that important and converged solutions can be obtained, but in reality, it is mathematically inconsistent, thermodynamically inconsistent. Also, what we can see is that with the constitutive model, given the temperature, pressure, composition, and compound IDs, we get the theta, that is the property, but also we get the derivatives. These derivatives are with respect to temperature, pressure, composition of the property. And in many cases, these derivatives cannot be ignored. If somebody is developing or using these days surrogate models, not using the derivatives would mean that the thermodynamic model or the surrogate model may not be thermodynamically consistent, because those derivatives are telling us whether the thermodynamic consistency, like the Gibbs-Duhem conditions, are satisfied or not. If they're not satisfied, then the behavior of the process will not be correct. At a certain point may be correct, but how they move from one point to another will not be correct. So one has to be very careful. And different versions of process and or product models are obtained depending on the system definition, model objects, assumptions, choice of the constitutive models, and so on. So let us see with simple examples how the model structure would be. This is a simple CSTR reactor. We have the feed coming in, we have feed and products going out, and we have a constant stir tank where the liquid is mixed. So the first thing is, what is the objective of this study? We want to study the effect of the inlet change, study the dynamic behavior, maybe that will help us to design the controller. And for this kind of study, we say that plus minus 10% accuracy is good enough. So based on this, what is the system description and assumption? We have a first order reaction. We assume that. We have perfect mixing. We have adiabatic operation, equal inflow and outflow. And we assume constant properties, which means that the properties will not change with respect to temperature, pressure, composition, and so we do not need to worry about the derivatives. But if they do change, then we need to worry about the derivatives. The constitutive equations that we would need here, that is the models, we need the reaction rates, the transfer rates, the property relations, the balance volume relations between the liquid and the vapor, and so on, and controller relations, equipment constraints, and so on. And then the conditions. If this reaction is taking place, is it in equilibrium? What is the control conditions? Are there any defined relations like mole fraction, summation equal to 1? What is the initial condition? Since it's a dynamic behavior, what is the initial condition? What should be the boundary conditions? All these are the conditions. Then, giving all of these, let's say we have derived the model, and then the model will consist of what we call the conservation equations, that is the balance equations. Then the constitutive equation, that is the property model. And here, since the properties are all constant, we do not need a model for it. We just need the single value, but we need a reaction model, and this is a kinetic model. And then we have conditional equations, the mass flow rate related to the volume, the enthalpy related to the enthalpy for the liquid and vapor related to the Cp as a function of temperature, then the flow rates related to the vapor. But the Cp values, these are thermodynamic properties. We are assuming that Cp is constant. Otherwise, we have to integrate the Cp with respect to T. So now we have got the models. What is the next step? And here, what I would like to show is that we talk quite a lot about model extension, model reuse, or also step-by-step modeling. So this can serve as an example to highlight all of these. So we have the CSTR model from before. Now let's say that we want to add some heating or cooling so that we can use this model at different temperatures. Also, we could say that this model that we have is one phase, but because of the temperature change, there could be two phases. So we need to add a two-phase reactor. And then we could say, well, instead of reaction, we can keep the two phases, and we can see without reaction, what would be the separation in the two phases. And then we could say that we have this model, which is with or without reaction in two phases. Can we use this as a module and create a network from it? So the first one, CSTR plus, all we need to do is add an energy balance for the jacket, add heat transfer from jacket to inside the tank through the wall. To create a two-phase, we need to add the energy balance, we need to add the equilibrium condition, add constitutive model for two-phase equilibrium properties. For two-phase tank without reaction, we need to remove the reaction and keep everything else. And then we can take the inlet and outlet and connect them as a sequence, either parallel or simultaneous, sequential or parallel or combination, to create a network. And this network actually could result in a multiple flash units or a reactive distillation or a non-reactive distillation. So starting from a simple CSTR, we can see that we can generate all these models through simple extensions and model reuse. So we can then think of how long will it take for us to develop from scratch to all the 5 types of models. Depending on the system that we are working with, from my experience, I've seen it can take as little as 1 hour or even less, or as much as even 1 year, depending on the system that we are modeling, or even more, or never. So, but can we improve the time it takes to develop the model? And that's where computer-aided modeling comes, that if we have a framework, through this framework, I would like to show that it is possible to reduce significantly the time to develop and use models. Let's first also define the domain, model domain. We are talking about models, mathematical models, and process models. So the first thing is we need a system by which we can derive the model equations. I would call it model generation. So if we define the system, from that definition of the system, can we get all the model equations that we need to represent that system? Once we have the model equations, we need to analyze the model equations to find out how many equations we have, how many variables we have, which variables to specify, which variables to calculate, what type of equations we have, all of this. I would call that model translation. Then once we have understood the model equations and everything, then we need to connect the model equations to a solver, that is a numerical solver, which will solve the equations and give us the values. That's what the simulator will do. The simulator already has a model, has a numerical solver, connects the two and gives us the solution. So that's the connection to the solver. Now, if we are developing a new model, how long will it take us to develop for the model generation? And then we need to verify that the models are correct, equations are correct. Then the analysis, which is the model translation. Then we have to write a code, a program to connect to the numerical solver, solve it, and then check. So that's all the steps that will take a lot of time. So a computer-aided system assists the user in performing the above tasks. And let us see how it will do it. But before that, let me first explain what the model generation is about. So we see at the top a flow sheet that is then divided into the unit operations, which is then divided into tasks, which is then divided into phenomena. So what we are doing is, as we are going below, from the top to one by one to the bottom, we are reducing the scale. And we can keep on reducing the scale until we have reached the end. Once we have reached the end, then we can say that reaction, we take a reaction model. Two-phase mixing, we take a two-phase mixing model. Ideal mixing, we take an ideal mixing model. And then these would be our phenomena models. The phenomena models are embedded into the task model. The task model is embedded into the unit operation model, and the unit operation model is embedded into the flowsheet model. So what we are doing is decomposing the system until we cannot decompose anymore. And then at the lowest scale, we have models, and for all the other scales, we have a procedure by which we can embed these models into the larger scale systems. So what we need is a method to decompose and develop the models at the lowest scale, and then we need a method to aggregate these and get the higher scale models. If we can develop a system like that, we can have a nice model generation system. Here is an example. On the left-hand side, you can see the balance equation, the constraint equation, the constitutive equation, the ontology is given. We go from left, and I'm just showing you 3 steps. Once we come to the last step, at that point, we have a corresponding model that we can use. And then once we have the model, we have the corresponding equations, and then we can continue with the developing of the model. So here is an example. If we just ignore the energy added in this, so we have a system which we call the shell, and this shell has 3 connections. 1 is input and 2 are output. As soon as we have defined that we have a shell with 3 connections, 1 input and 2 output, we can go to the balance and we can say, from the balance, give us the mass balance equation, give us the energy balance equation. And it's simple. On the left-hand side, unless it is at steady state, it will be given in terms of accumulation, and then input is plus, output is minus. So energy coming in, energy going out, mass coming in, mass going out. But to calculate any of the values on the right-hand side for the variables, we need the constraint equations, constitutive equations. And then we need to define what is happening in the shell. So then we define what is happening in the shell. There are 2 phases. That's a vapor liquid. They're in equilibrium. There is no reaction. The vapor is perfectly mixed. The liquid is perfectly mixed. So we then take from the library the model to calculate vapor liquid equilibrium, the model to calculate the equilibrium constant, and so on. And then we embed them into the equilibrium model, and then we embed the equilibrium model into the mass balance and the energy balance. So that's how the model generation would work. Now, if we automate that as much as possible, not 100%, then we could have a computer-aided modeling too. So on the left-hand side, we can see that there is problem definition, system characteristics, problem data. That is best defined by the human because they know which is the problem they would like to solve, that is the system and the corresponding model objectives. What are the system characteristics that have to be captured, and what are the data available? Once these are given, the rest of them, model construction, model solution, model verification, all of these the computer can do. We do not need to write any programming code. As soon as the equations are written, everything else the computer can do. Even computer can write the equations. And if one looks at how much time one spends in developing a model, it is the green part, which is 80% of the time, and the top blue part is less than 10%. So we can save a lot of time if we can develop a computer-aided modeling system like that. These days, maybe even deep learning or machine learning can help us with the system characteristics and problem data. So once we have used this system, the result would be a model object. And this model object then can be used with a calculator or a solver. It could belong to a library of models from which people can take whichever model they need and then connect with the solver through the tool that I've shown. or they can make customized simulator. Note that for all the steps after the model object that they have got, no programming is needed, and therefore a lot of time spent on developing and testing and writing the equations, all of these things, and even analyzing the equations. These are all saved. The time is saved because the computer can do it much faster than the human. So now let's see some of the equations so that we can understand a little bit better how the system would work. So if we are solving any process engineering problem, usually we do optimization. So f of bj is the objective function that we may want to minimize or some cases maximize. And so we have a multi-parametric objective function. The terms S are related to sustainability, H are related to safety. Even though I'm showing them as part of the objective function, I would recommend to use them as constraints rather than in the objective function. Then equation 2 is process constraint. For example, what should be the conversion, what should be the product purity, and so on. Then equation 3 is the whole system of process model. And within the process model, equation 4 is the embedded property model. Equations 5 are constraints on the variable, limits on temperature, limits on pressure, limits on valve opening, so on. Molecular structural constraints is equation 6. If we are using catalyst or solvent or refrigerant, what would be the molecules we would like to use? And finally, if we have a network, which is a process flow sheet, what would be some paths that are not allowed? So we have real process variables, X, integer decision variables, Y, process design variables, U, D is the process input variables, theta is the property, B, C, D, etc. are coefficients. Depending on the problem or the system, we can have a system of algebraic equations, a system of differential algebraic equations, a system of partial differential algebraic equations. If we also do the optimization, then again, depending on the variables and system, we can have linear programming, nonlinear programming, mixed integer linear programming, mixed integer nonlinear programming. And once we then have analyzed the model and the system, we need to find a solution. That is, we need to connect our model to the solver. So we need a solver, and the solver can help us to solve in the direct way, that is direct solution. You call the solver, give all the equations, everything is taken care of by the solver. Or you can help the solver by decomposing the problem into smaller sub-problems and solve in a given sequence, or hybrid, combine the decomposed and the direct solution. Which one is better depends on which problem we are going to solve. There can be as little as 7 equations, as much as 7 million equations, depending again on the problem we want to solve. So here are some examples, very briefly, to show you what kind of problems we can solve. The 7 equations are there. On the left-hand side, in the bottom square, you can see a product represented by equations 4 and 6, product design. Process design represented by equations 2, 3, 5, 7. If we want to optimize the, the design, in both cases, we need to use equation 1. So then let's see, if we want to do process simulation, it's just equation 3. If we want to do process optimization, we also include equations 1 and 2. If we want to do product evaluation, just similar to process simulation, it is 4 and 6. If we want to do the optimal product, we add the objective functions 1, 4, and 6. If we want to do product, but not detailed process, implicit process. So in this case, we have the product property models, and we have simple models for the process. That would be equations 3, 4, and 6. But equation 3 would be a simple model. If we want to solve everything, then we take equations 1 to 7. With respect to the solvers, if you look at the paper here, a recent paper that came out in Computers and Chemical Engineering, the next generation for process systems engineering, there is a very nice list of solvers that can be used for different kinds of problems. So what we have seen up to now is that depending on the problem, we will have different sets of equations that we need to solve. Also, and that we will have phenomena models, that is the property models embedded in the process model, and the process model can have different forms. So what this slide shows is that in the process life cycle, actually we can see that we need different forms of models, but some models do not change, other models change. And that's the reason why we have to think of the importance of thermodynamics and the phenomena that is occurring in the processes that we are studying, because while the process model at different stages in the life cycle will change, the phenomena model will not. If the same chemicals are being used at the same conditions, then those properties are fixed, and the model that gives those properties are fixed. But in process engineering, we are using maybe steady state model. In detail engineering, we are using more detailed model. In production, planning, operation, we are using dynamic model, open loop, closed loop, and so on. So all of this model will change, but the phenomena and how the chemicals react and behave will not change. So that is why the phenomena models are very important, and one should not make unnecessary assumptions related to them. So what kind of models can we get? Mechanistic models, fundamental models, first principle models, black box models, gray box models, which is the most common, machine learning based models these days, and many more. These models can also be further refined in terms of simplified models, reduced models, local model, surrogate model, hybrid model, and I will discuss them a little bit later. And then one can also question, among all these models, which are predictive and which are not. Correlation would not be a predictive model. They would still be valid under the conditions during which those correlations have been obtained. But if we want to solve synthesis problems and want to get new innovative solutions, we need predictive models. So let's see now the issue of simplified model, reduced model, local model, surrogate model, and so on. So let us say what you see on the left-hand side. We have the process, the real process, and the model of it, and the constitutive models embedded. We want to optimize this process. So it's a process optimization. So in order to optimize the process, we need to calculate the objective function for a given set of values of the design variables. So we have the process, we say these are the design variables, these are the variables we want to test. So we give this, then the optimizer needs to calculate the objective function. And based on it, we'll find out objective function and constraints, whether the solution is optimal or not. To do that, we can do it in two ways. From the optimizer, it will go to the objective function. I'm not showing the other input-output relationships. From the optimizer, we go to the objective function. The objective function will need to know the process variables, X, the specification variables, Y, and from those, it will be able to calculate the objective function and check the constraints. It can be obtained from online data of the process or from a model, rigorous model that represents the process. So that's one way of solving it. And we will iterate until we have the objective function, G and H are the constraint equations, until all of these are satisfied. However, the host model, which is the rigorous model representing the system, may be complex, may take a lot of time to solve. And so people have said that we will replace the host model with a model I that can be different types of model. And, and what we will do is this model I will represent our process under certain conditions. And this model is not as complex as the host model, so it is very fast. And so we can save the computing time. So then the optimizer, instead of going to the process of the host model, will go to the model I and get the objective function values, and we will get the solution. But are these solutions correct? So what people did before was that they used a simple model, which also they call local model, in the blue loop. And then when they got a solution, they did a calculation, one iteration on the green loop. And if the two numbers matched, then convergence was obtained. If not, then they will use the green values to update the model in the blue loop and then continue. So that was the way people did when they used model simplification. Model simplification can simplify the constitutive model or the process model. Model reduction will not simplify the constitutive model, but reduce the number of equations in the process model, usually. Local model, again, is what I described, is that maybe the constitutive model or maybe part of the process model, which takes time, would be converted into a local model. And when they're doing the optimization, they will use the local model rather than the host model, and thereby save time. So in all of these, the main thing was to save time, but also it was to make sure that the results are correct and consistent. So convergence with the local model would be checked with the rigorous model. These days, also surrogate model has been proposed. As far as I understand, the surrogate model does not require the two loops. The surrogate model is developed so that it can represent the host model within the conditions that they have defined. I'm not sure if that is possible for the thermodynamic models unless the derivatives have been taken also, and the consistency test, thermodynamic consistency tests have been done. Otherwise, it would be quite dangerous to take only the property values and create a surrogate model. But there are other ways to do it. I'm not saying that this is not possible, but one has to see. Also, one should note that if one can replace well-defined thermodynamic model with a surrogate model that represents the system under all the conditions of temperature, pressure, composition, then maybe they have developed a new thermodynamic model which is much simpler than the original. As far as I know, things like that has not happened yet. So let's look at also, we looked at in the previous example, the U are the design variables, but we also have the phi, which are the process parameters. So if we have a model with parameters, we can also set up an optimization to solve for the parameters. That is, we have experimental data for Y, and then we assume the values of the parameters, and the optimizer gives us the optimal solution of the parameters when the summation of the least squares or some other objective function is minimized or maximized. So we have the molecular structure. The molecular structure gives us primary properties. For every molecule, there is only one value of critical temperature, pressure, etc. That helps us to generate the PVT behavior, pressure, volume, temperature behavior. But to calculate this, we need the interaction parameters. So we have parameters that needs to be fitted with measured data of pressure, volume, and or temperature. And in order to do this, in addition to the PVT relationship, we also need the vapor pressure. That is another property. So we need the equilibrium properties, like the phase equilibrium properties, like the fugacity coefficient, activity coefficient at different temperature, pressure, composition, as well as the vapor pressure. And all this fugacity as well as the vapor pressure are functions of temperature, pressure, composition. And the way they will change, we cannot arbitrarily make them change in a certain direction. There are consistency tests that needs to be used to verify that they behave in the way they are supposed to. Otherwise, the thermodynamic model will be inconsistent. And what we see from this, compared to this cartoon in the middle, we start from two sides, and in the middle we need a miracle. The miracle actually is the parameters that we put in. The interaction parameters in the equation of state or in the activity coefficient models or other models are all parameters that help us to perform this miracle. So those who are doing, or the kinetic parameters in a kinetic model, those who are doing this regression, they're performing the miracle every day. Then the question of predictive and correlation, I'm using a thermodynamic model to explain it, but the same will be true for many other systems. And the question is whether the parameters can be extrapolated or not. So what we see on the left-hand side, the different circles with colored circles, green, blue, yellow, red. These are combinations of atoms. So the yellow is CH2, 1 carbon, 2 hydrogen with 2 free bonds. The green is 1 carbon with 3 hydrogen, 1 bond is free. The red OH, oxygen and hydrogen and 1 bond free. These groups of atoms can be combined together to form molecules like 2-methyl, 1-propanol or ethanol. Now, when we want to calculate the properties of molecules, all we need to do is to find out which groups are needed to represent the molecule and take the contributions of each of those groups. It does not need to know to which compound they belong to. And that is how we calculate whether it is pure compound property or phase equilibrium property like activity coefficient. It only needs to know what is the interaction between the green group and the red group, but it does not need to know whether that interaction is for propanol or ethanol. So that's why it is a totally predictive model. On the other hand, if we take the models like the NRTL or UNIQUAC or SRK or Peng-Robinson or things like that, they need molecule-molecule interaction. They do not use the group-group interaction. So these models are also predictive with respect to temperature, pressure, composition, but they're not predictive in terms of molecules. So for every new mixture, we need those interaction parameters that we do not need for the group contribution. So that's why it's a very powerful predictive model. And also we can see that if we want a model with respect to temperature, pressure, composition, the molecular models are already available with consistent expressions that will give the correct derivatives for temperature, pressure, composition. If we replace it with arbitrary derivatives, it will be totally wrong. The use of machine learning, here is an example coming from a recent work that I've been involved with. The red part is the performance of the model developed, that is the parameters developed from machine learning, and the blue part on the left is developed, the parameters developed from conventional regression methods. Obviously, the machine learning is very accurate. You get nearly 90% of the molecules fitted to 1% error, which cannot be obtained with the simple group contribution or standard regression. So this is good that we can increase the accuracy of the model. But what is the expense? In the simple group contribution model, the contributions that you see, C superscript F, C superscript S, C superscript T, these are different groups of first order, second order, third order. Every contribution that is group has one contribution. And if we have, let's say, a total of 424 groups, all we need is a table of 424 parameters for one property. And then we put the contributions in this simple model and we calculate it. Because of its simplicity, of course, it's not that accurate. We can get 90% accuracy for 10%, within 10% error. But machine learning gives us 1% error. So what is the cost of machine learning? Here is an example. In order to calculate the contribution C, F, CS, CT, we need to do some matrix multiplications. And those matrix multiplications, NP times NC is the weight factors. And NP is the value that is generated through optimization or by trial and error. It can be anything between 10 to 20. And NG is the number of groups. So what we can see is that to do the same calculation with the machine learning, we need at least NP equal 20 and NG equal 424. So 20 orders of magnitude of parameters we need in order to get the 1% accuracy. And it is not a simple expression, it's a complex expression. If one writes those equations, it may need 3 or 4 pages to write those expressions. So in one case, we have very simple calculation, in another case, we do not. In the case we do not, we have high accuracy. In the case which is simple, we have low accuracy. The thing also with the simple model is that it can be easily inverted. From the property, we can get the molecular structure. It is not that easy to, or let's say more work is needed to do the inversion from the property to get the molecular structure. That is a good advance, because now we can say that we have really accurate prediction of the properties, because it's group contribution based. Another thing to look at is reality versus virtual reality. Most of the problems we are solving, or let's say products and process we are designing, is based on experiments. And what happens in the scheme above the dashed line, we have a system, we study it, do experiments under different conditions. We like one experiment, and then we say that is our final solution. That is our solution, and we develop the product or the process. But the question, of course, is, even if it satisfies our requirements, is it the optimal? It is not guaranteed. On the other hand, the system below, the virtual reality, instead of doing the experiment, we have a model of the system. We do virtual experiments. We arrive at a solution. And then we can say, is that the best solution? Well, we don't know how good the model was. Within the search space of the model, it could be the best solution. Is it accurate? We need to check with the experiment. So we then could say that we will do the virtual experiments first, generate alternatives, and then we will do focused experiments with respect to the system. So at least we could say that even if it is not guaranteed optimal, it is verified and we have saved time. But in order to have a guaranteed optimal, we need to have model that is predictive. And here, the data that we collect from the system, we could use that data, and then we could use it for modeling and apply machine learning. We can get very accurate models, and we can get also extrapolation from the parameters. Then we will have models giving us innovative solutions. We will still have to verify by experiments, but since we are telling exactly do the experiment at these conditions, then it can also be focused experiments. Also, to do the experiments, we can, from the experience of the virtual experiments, we can guide and provide insights for design of experiments. And then we can add tools for data collection, storage, sustainability, and environmental impacts, then tools for data analytics, modeling, tools for workflow for finding solutions, model-based solutions of synthesis, design of experiments. And then we can see that we can have a very nice integrated approach that combines both experiments and model-based systems. And that is all what we should be aiming for also. I will go back again to the simplified, reduced local surrogate models. And I've explained all of this already before. So what I would suggest is the following. In the 1980s, when model simplification, reduction, local model were very hot, what people were doing was the host model was cubic equations of state or UNIFAC or combined equation of state and gives energy models. And the local model would be correlations with derivatives. So correlations and derivatives would, of course, be much faster. But now computers, with new computers and faster computers and all these things, we do not need to save time with the equations of state or the combined equation of state GE model. If you want to actually compare the time needed to do a flash calculation or one iteration of the flash calculation, in order to have some time that can be compared, one has to solve these problems 1,000 times to actually have some comparable times. Otherwise, it will be too small to measure. So, which kind of problem should we solve? I would propose that if the host model is, for example, PCSAF, SAF, Cosmo RS, and things like that, that would be very expensive to put in an optimization loop. So in that case, we need a simpler model, and the simpler model could be the cubic equation of state, UNIFAC, NRTL, and others, which would be much, much faster. But the host model, the data of the host model will fit the parameters for the local model. And if we can do that, I think we can get much, much better results and using very accurate property models, which are needed for many of the problems we want to solve. Some final comments. At the ESCAPE conference, ESCAPE 31, recently in June, in online meeting in Turkey, there were 3 plenary speakers. Professor Reklaitis talking about PSC challenges in advanced pharmaceutical manufacturing, Mark Olivier Coppens on nature-inspired chemical engineering, and Stratos Pistikopoulos on circular economy, a challenge and opportunity for PSC. What I want to highlight is what they proposed as not the only one, but among the research challenges, all 3 mentioned modeling and model-based systems. And these model-based systems included mechanistic, data-driven, ML, surrogate, hybrid, etc. But modeling and model-based systems are very important for the research challenges currently and in future. And what also they said, if we can attain this modeling and model-based system objectives, it will reduce development time, solve problems faster, robustly, reliably, reduce cost, and shorten development time. So this is also what I've been saying with respect to why we need model and model-based system. Here is an example of a versatile product process model. The different colors, I will not go through all of them, are different submodels that we need to define the system we want to study. And for any different system, if we have in the library collection of models for each of those colors, we can retrieve them, put them together, and very fast we can have the product process model that we need. Another one is quite interesting also is the case of multi-scale product process design. You see a reactor at the large scale, and then within the reactor, we have the particle, and then a swarm of particle, and then a single particle, and the structure of the particle on the surface. How are these related? This was very nicely described by Professor Charpentier. First, identify the desired end-use properties of a microstructured product at the small scale, and subsequently control the product quality and production efficiency by manipulating the microstructure formation at the process scale, leading not only to a novel product, but also to less waste and lower energy consumption. Again, if we can do that, we can solve the product process design problems as well as find innovative solutions. Something to think about. The curve on the left-hand side shows what kind of tools could be important in the next 20, 30 years. Modeling and simulation is very high, big data is very high, cloud computing is very high, and machine learning is also among the top. Also, at the same time, we have to think of that if we have model and we have parameters, then there will be uncertainty in the model, and we have to be careful when we apply the model, we do not come into this situation. Finally, I would say what are the things that I learned from Professor Sargent. As I said, the two very important statements that has defined my research career, my research work, are what is PSE and what is a systems approach. But in addition to that, I also learned from Professor Sargent, in the way that he motivated me, I should also motivate my future students. That means my past students now. I hope I have done some of the motivation, not as much probably as Professor Sargent, but hopefully some of the students were motivated. Also, he always had time for a meeting with me whenever I needed to discuss anything. Meeting students regularly and discussing the work is very important. Serve the PSE community. I've tried my best to serve as much as possible. Many more. Also in PSE or within PSE, understand the importance of models and model-based systems. Model is the fundamental core of my work. Everything starts with the model. The solution should be generic. Try to find generic solutions. That means the model should be applicable to as many systems as possible. The solution technique should be generic so that even though the problem is different, the solution steps are the same so that we can have wide applications. And most important, follow a systems approach. And so again, I would like to thank Professor Sargent for giving the supervision for my master's and PhD project, teaching me the importance of process systems engineering and systems approach. And I would like to thank all of you for listening to me. And if you are interested in the list of references, the last slide has the references, but before that, I would like to advertise a little bit. If you're listening to this before 16th of September, there will be a webinar on systematic and rapid model development on 16th September, a 4-hour session. You're most welcome to attend. The participation is free, but registration is needed. And then the last slide is the list of references. This lecture, the slides can also be downloaded from the PSE for Speed website. So thank you very much. And if you have any questions, please feel free to contact me and send your questions. During my actual live presentation, there were a lot of questions that I answered. Unfortunately, I don't have the recording of that. With that, I will end, and thank you very much again.